Hello and welcome to Coffee and Control, the podcast in which I find fascinating people working within the field of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is a lecturer and researcher at the University of Southampton. So, just like Chris Freeman, who I interviewed in episode 1, my guest this month is also one of my PhD supervisors. However, I hadn't read a ton of her papers before researching for this episode, but as it turns out, her research is so interesting. It really opened my eyes to areas of control I had no idea even existed, and it was so lovely to be able to sit down with her and ask all of the questions that I wanted to ask about the things she's been working on in the past, what she's currently interested in, and how she ended up where she is now. So get ready to hear all about modelling the brain, fractional order systems, control applications in cancer treatment, and why interdisciplinarity is key to having a real-world impact. With my guest, Dr Zehor Belkhatir. Can I get you to start by saying your first and last name and then a few sentences introducing yourself and your research?
So my name is Zehor Belkhatir. I'm a lecturer in ECS in the University of Southampton. My research area is really at the intersection of control theory, data analytics, including machine learning, and applied mathematics.
Okay. So I'd like to start by getting an idea of what drew you into control in the first place. So you studied an engineer's degree, which I assume is the equivalent of kind of undergrad bachelor's degree in automatic and control systems, and then went on to a master's. What led you to doing that degree?
So I think the education system I came from, it's a little different from the UK system. It follows closely the French system. I did what we call the École Polytechnique or National Polytechnic Schools, which is basically an engineering school. Mm-hmm. It's 5 years of studies there. It's equivalent to a master, I would say, here, or like a little bit more. The philosophy of like those engineering schools, you get into them, you do 2 years, which is common. And at the end of the 2 years, like depending on your ranking, you have to choose the specialty that you're going to go with. Why did I choose control engineering? I think for the maybe the simple reason. Since I was in high school, I was really fascinated by mathematics. But I didn't want to do abstract mathematics. I wanted like an engineering degree that has quite a lot of mathematical foundation. And it turns out that control engineering, doing a bit of research at that time as an undergrad, it was that area that you can look at it as applied mathematics, but it is interfering in lots of application because you can find it in biomedical applications, in more robotics application or more electrical applications, but it does have that mathematical foundation or theory into it. So I think this is why I chose control engineering instead of electrical engineering from the beginning.
So after your degree, you then moved to Saudi Arabia for your PhD. There's a lot more technical things I'm going to ask you about later. But firstly, I'm interested in kind of how the PhD came about. Like, why did you move countries?
So I would say that that's one of those hardest questions because like usually after we finish engineering schools in Algeria, like it's really easy to go in France and carry on master there because it's the same education system basically. I did have that chance because I had a scholarship from one of the universities in Paris. But why I moved to another country, I think what helped me to move to Saudi Arabia instead of accepting my scholarship to France, it was that I did an internship my final year, and that helped me to see like what is available in terms of research capabilities, like seeing the opportunities that were there in KAUST, King Abdullah University of Science and Technology, as part of my master's studies, helped me to say, okay, now I think I'm ready to start my PhD journey there and carry on the research I have started in my master.
As far as I understand, your PhD thesis was concerned with the hemodynamic response of the brain, so looking at different ways to model it and develop different types of estimators. So could you first explain briefly what is meant by the hemodynamic response of the brain and why it's important to be able to model it?
Sure. So that was the key application of my PhD research work. And so the key question was, how can we infer or how can we estimate the neuronal activity inside the brain without, of course, opening the brain and then measuring it directly. And the straightforward approach from the control theory perspective, or what we call it an inverse problem perspective, it's to be able to model the relationship between the neural activity inside the brain and the measurable outcome, which was fMRI, functional magnetic resonance imaging. So if we can have the output easily measured from fMRI machines, and we have tools from estimation and modeling that will get us to the input, that will be really, I would say, an efficient way to understand a little bit what's going on inside the brain. And that was the main application of my PhD.
I just want to jump in here with a little bit of background for anyone not familiar with fMRI. So, regular MRI, magnetic resonance imaging machines, are used to take structural images of the inside of the body, so in this case, the brain. fMRI scans are specifically used to look at the function of the brain and highlight activity in specific areas. And this is possible because an increase in neural activity increases the amount of oxygen in those tissues, which can then be detected by an MRI machine. But as Zehor is explaining, there's a very complicated relationship between neuronal activity and what a clinician can see on an MRI machine.
We know that the brain is very complicated, and it's really important to know both the spatial dynamics and then the temporal dynamics. And this what has led me in my PhD to work on a type of system which is infinite dimensional systems instead of just looking at finite nonlinear dynamical systems. So it's really important to measure or to understand what's going inside the brain with an easy or an accessible measurement, which is not invasive, but we need to add a little bit more into that in terms of modeling, inference, and inverse problem solutions.
So you mentioned infinite dimensional systems. Could you explain or kind of define the difference between finite and infinite dimensional systems and why it was important to use infinite dimensional modeling in your work?
So infinite dimensional system, if I would like to describe it, or you will see it in a lot of papers as partial differential equations, but it's not really restricted only to partial differential equations or distributed systems. It can include other types like fractional order systems. And why those are of infinite dimension? Because your state, it's not living in finite dimensional space like Rn, but it's living in an infinite dimensional space. If you have, let's take an example of partial differential equations where you have the spatial dimension. Like this dimension most of the time lives in Lebesgue spaces or Hilbert spaces, which are of infinite dimension. And this is really the key difference, I think, between finite and infinite dimensional system. Like the finite one, basically, you have only the temporal dynamics of your equation, which is evolving in time. That's what I would call a finite dimensional system. Mm-hmm. And again, I have looked at two types of infinite dimensional system in my PhD. The first one, which was partial differential equations, where I have the spatial component. And the other one, it was fractional order systems. And you can look at them as like ODEs, but instead of talking about first derivatives or second derivatives, you talk about derivatives or fractional orders. Mm-hmm. So those are the two types I have looked at in my PhD.
Okay, so we're going to come back to discussion of fractional order systems later in the episode, but just a quick interjection to say that these are really cool, very complicated, lots of clever maths that is explained very well in Zehor's papers in this area and also in her thesis. So I'm going to focus a little bit too much on fractional order systems in this episode just because I find it really, really interesting, but hopefully you'll enjoy it. Okay, so as well as modelling, your thesis also focused on creating estimators to estimate system state, but then also unknown inputs and parameters. Why is the development of appropriate estimators so important when dealing with the types of biological systems we talked about in particular, and then kind of more general biological systems?
So the estimation problem, if you look at it from pure estimation, especially for biological systems, it's really important compared to when you do like estimation for control purpose. Why is that? Like I will give you the example of the hemodynamic response in the brain. So the input usually to a control system, it's what you design to achieve particular performance. But the input for that particular biological system, it was a quantity that really we can't measure, not invasively. So it's really important that our estimators converge, or we have guarantees that they will converge to the true input. And this is sometimes like it's not really necessarily to prove when we are doing control. As far as we are achieving the control objective with an unknown input that we don't know, that can be enough for particular applications. But for biological problems in particular, it is really important that our estimators have some guarantees that whatever we are estimating in terms of input, unknown input, and then parameters are expected to converge to the true values because of their biological meanings, and they can tell us a little bit more about the biology or what's going on inside the brain. And that's the difficulty from the control perspective or the estimation point of view, because you don't need to prove convergence just for the state, which maybe it's more straightforward, but you need to make sure that your estimator for the input and then the parameters are also converging to the true values. So that's really what is specific in terms of having estimators for biological systems. And of course, it depends on the biological system you are working on. But for the particular one I was talking about, like we don't have control input, but we do care of having a good estimates of the biological variables.
So we've talked already about the inputs and the states. Could you explain what those represent with the hemodynamic response of the brain and the clinical or any other benefits that are gained from knowing what those values are?
Sure. So again, for the biological application of the hemodynamic response in the brain, the output was what we call a blood oxygen level dependent. This measurement, usually we get it from the fMRI modality, functional magnetic resonance imaging modality, which is relatively and non-invasively easy to get. So that's the output that we are relying on. The input to our system, we have two stages of input because the system, it was a cascaded system. The first input we were looking at, it was the neuronal activity inside the brain, like how like the neurons are fired or inside the brain. And the second important input, it was what we call the cerebral blood flow. So what's the blood flow inside the brain? So because the system or the model was very complicated, we took advantage of the structure of the system because it was in cascade. So we can solve the second estimation problem going from the output into the input, which is the cerebral blood flow. And then once we have a good estimate of that, we can say, okay, now we are ready to solve the first estimation problem and then get enter the neuronal activity. So this is how we dealt with that problem. Otherwise, it was very complicated to have only one estimator that guarantees our both unknown inputs converge to the true one. If you don't do that, like there is no biological relevance of our estimates, and we do care in that particular application about the biological relevance about the estimates. It's not about just having an estimate, but it's really about having a good estimate. So the short answer to your question, that was what we have as an input and output for that particular system. Neuronal activity, the first input, getting to the fMRI measurement.
Why is it useful to know what the neuronal activity and cerebral blood flow is?
For example, like let's take cerebral blood flow. For instance, if you look at the shape of the cerebral blood flow, there is like a dip at the end, like it goes negative and then it goes back to constant value. And that's an initial dip. Usually it lasts for 1 second, approximately 1 to 2 seconds. Let's say if we have an estimate where we don't have that dip, or that delay or that time instead of the dip, it's too big. This can say that there is something wrong maybe with that patient. So if you estimate cerebral blood flow, which doesn't look like normal, you can give it to a specialist. Of course, we are not specialists in the medical field, but we always try to collaborate with people in the field. If you say, okay, this is a patient, this is what's our estimate for his or her cerebral blood flow, what do you think? And from his experience, he would say, there is maybe a problem or not with that patient. So it really helps at this stage. So instead of the clinician going and then doing a more invasive measurement of those variables, I would say, no, give me the fMRI and I have good enough estimators that will digitally help you to get a cerebral blood flow and then take your conclusion from there. So That's why it's important, or how it can be used in the clinics. Okay.
I was looking back through your early research and noticed that a few of the papers that you wrote at the beginning of your PhD were on the cardiovascular system. So I was wondering what led you to applying the methods you developed in your PhD to the brain rather than the heart.
The work I did on cardiovascular system was part of my master project. I was still, like I said, in École Polytechnique doing my engineering degree, but I did an internship of 6 months in KAUST before deciding to go as PhD. And I think the simple reason for the cardiovascular system, my PhD supervisor, that she has some real data and she worked previously on cardiovascular system. And she wanted someone to carry on the research she has started. That's how I got into the working into the cardiovascular system.
So the specific paper that I was referring to here was the 2014 ECC paper that Zehor wrote on using observers to detect cardiovascular anomalies. So basically using observers to work out whether the valves of the heart are opening or closing normally. I'm going to link to that paper in the show notes. Zehor also contributed to a book chapter about modelling the cardiovascular system using hybrid dynamical systems theory. And I really wanted to discuss this in this episode, but we ended up running out of time. But the basic idea is that the presence of valves in the heart means the heart has 3 discrete modes of operation, and then within each mode, the state evolves continuously, which means that you could apply kind of theory of hybrid systems to be able to model this behavior. Again, I'm going to include a link so you can read up on it more if you're interested. I thought it was very cool.
Now, why I did switch in my PhD? Because I wanted, to be honest, I wanted to touch upon in new types of systems, which is the partial differential equation and fractional differential systems. And I met a researcher, Kevin Aquino. He is the one who proposed the model for the hemodynamic response in the brain. And I got somehow inspired because the model he proposed, it was based on analogy he did between the hemodynamic response in the brain and porous medium modeling. And I met him in Berlin. Like I remember it was one of those conferences where he presented the type of model like they worked on to model the normal activity from fMRI. And I think when I saw the model, I said, this is an interesting model, and there is quite of like challenging estimation problems in here. And this is why, like you see in my PhD, I started my PhD finishing my master work on cardiovascular system. If you see my first publication, it was really at the beginning of my PhD where I tried to finalize my master work and then publish it in conference. And it was that period where I started to read more into research, like, and see what's the next problem I can tackle. I think sometimes you have an area that you are working on. For example, I was interested in estimation problems, like from the theoretical point of view, independently of the application, because again, the application, it didn't come at the beginning of my PhD. But I really wanted to have new methods in estimation for my PhD. Now, whether that will be applied to the cardiovascular system or another system, I didn't plan for it, but it came from the research discussion.
So we've talked already a little bit about fractional order systems, but I'd like to go into that in more depth. So a large chunk of your thesis examined fractional order systems or fractional order models, and you've kind of continued to work on that since. Can you give an overview of what a fractional order system is and why it's useful to model physical systems using them?
Of course. So fractional order system, if I want to define it, it's an ODE where you have a derivative of fractional order. Instead of having a first derivative, second derivative, or an integer order derivative, you have derivatives of fractional order. That's what's fractional order systems. Now, if you look at the literature, you'll find a lot, like there is a property of those fractional derivatives. And their property is they are not local operators. Like if you think about first derivative, you can take 2 points, you take the slope, and then you can have an estimate of the first derivative. A fractional derivative, if you want to measure it at a particular point, you will need the whole history from minus infinity to that point to be able to compute the derivative, fractional derivative point. So it has, we call it a non-local property, and this property, it turns out to be very useful in modeling a lot of phenomena, especially in the biomedical field. For the cardiovascular system, it has been shown having fractional derivative helps to capture what's going on before. Now, why did I use it for the hemodynamic response? To come back to your questions, why that was relevant for hemodynamic response. The hemodynamic response, like I mentioned previously, two inputs, the neuronal activity and the cerebral blood flow input. It is known that biologically there is a delay between the onset of those two inputs. So if the neuronal activity fires at this point, you need to wait 1 second and a half to 2 seconds until the cerebral blood flow starts increasing. And delay systems, usually like it's non-local, they have that memory effect. So there was a model, a second order oscillator model to relate neuronal activity to cerebral blood flow. And we have showed using some real data provided to us that if we have a fractional oscillator, second order oscillator, instead of an integer second order oscillator, it's allowed us to capture much better the delay between cerebral blood flow and the neuronal activity. And this model, it didn't exist, but it was an improvement of an existing model. And we have proved that it's better using a large data set of different neuronal activities and CBF that was provided to us.
How did you first learn about fractional order calculus, and what was your reaction? Because I was kind of mind blown when I read your papers.
God. There was a book, like I don't remember like the author, but there is a research group in France who are specialized on fractional order systems.
The book that Zehor is referring to here is Fractional Differential Equations by Igor Podlubny. And when we talked about this after the interview, she also recommended a few other books she found helpful, as well as some MATLAB toolboxes for fractional identification and control. So I've left a link to those in the show notes.
To be honest, it takes me quite some time to understand the theory behind it, especially because we have some facts for integer order derivatives. Like we know this is what is first order, this is what is second order. In the fractional world, you have 3 definitions or more of what is fractional derivative, and they are not necessarily all equivalent. It's really important to understand each definition and what is really the difference. Like I said, there is a capital definition, there is a Riemann-Leibel definition, there is a Granol definition. The 3 of them can be equivalent, but given some assumptions and conditions. And that's what was bothering me at the beginning when I was learning about fractional calculus, because I said, I know that the first derivative, this is how I can define it. But now it's very tricky. If I change the definition, maybe the proof won't be working. And this has led me to dive a little bit more into the definition until I found out that there is a type of definition which is called initialized fractional derivatives. So what is initialized derivatives? We know that the time starts from 0. But like I said, we know that fractional calculus is non-local, so you need the history from minus infinity. So those initialized definitions, they will tell you, instead of having an initial condition at t equals 0, you can think of having an initial function that you define from minus infinity to 0, so that when you arrive to 0 at that point, you are sure that all the definitions are equivalent. So that's a little bit more difficult definition, because you don't think about only the fractional derivative, but you think about what type of initialization function you need to have at the beginning. And it was quite interesting, I would say. It wasn't easy at the beginning, but I think when you dive into it and then into the theory, you will discover a lot of questions that needs answer, and then this will take you to something else. But it was quite interesting and enjoyable learning phase for me to learn about fractional calculus.
You've mentioned already modelling the neurovascular coupling and arterial compliance using fractional order systems. So I was wondering, are there any other biological systems that either people have worked on with fractional order systems or that you think it could be applied to?
There is a cardiovascular system. There is a Windkissel model, which is basically a model that takes the arterial cardiovascular system and then put it as an electrical circuit. It's called Windkissel model. Now people are trying, instead of talking about a capacitor, like a normal integer capacitor, they are talking about fractional capacitor. And that's really an area, I would say, one of the largest areas where fractional calculus has been proved to be better than integer order. And like just by knowing the alpha, the fractional orders, it has been shown that this can be linked to how elastic are the arteries.
Going back to the topic of estimation that we were talking about earlier, part of your PhD focused on creating higher order sliding mode observer to estimate state and unknown inputs. Could you give a brief summary of what higher order sliding mode observer is and kind of why that was useful?
Sliding mode observer, it really came from an observation that people investigated lots of sliding mode observer for integer order systems, but none of the studies were able to do the extension. And I said, why? I worked on sliding mode observer in my master. Why there is no extension to fractional order systems? How difficult it's to generalize the proof from the integer order to the fractional order. It wasn't straightforward, but that's what got me into the sliding mode observer. It's really by a curiosity, because I know sliding mode observer, and I was working on fractional system. I have an input that was unknown, and I couldn't find much in the literature of observers for fractional order systems with unknown input. So the straightforward observer that I knew about was sliding mode. How can I generalize it? But when I did generalize it to fractional order systems to estimate the input, now I had one more challenge, which was I don't know usually the fractional orders in my system. Okay, so can the sliding mode estimate both the input and then the alpha? That wasn't possible, at least after a couple of months of research. It's really hard to prove that you can have the sliding mode observer generalized to not only estimate the input, but tell you what's the fractional order of your system. And this is why, for the hemodynamic response later on, I switched to another type of estimator, which was modulating function. Because with a modulating function, I had that capacity to not only estimate the input, but can estimate the fractional order. Because this is not something biological that we can measure what's the order. It's something that helps to understand the biology. So we need to estimate it and have value of it.
I think you've probably mentioned some of this already, but what are the particular challenges faced when dealing with fractional order systems?
I think the key challenge, again, it's about the initialization function and how this is affecting your estimation. Let's say if I take an initialization which is 0, or I take an initialization which is flat, just equal to 1, would that have a big effect on my estimates? And this is a big challenge, I would say, in the field up to now. Can we have one homogeneous definition for fractional order system where it combines whatever exists now and they are all equivalent? I don't know, to be honest, the answer up to now. There is quite some few researchers working on this initialized definition. So that's the biggest challenge. Like in ODEs or nonlinear differential equation, you know that if you start with an initial condition x equal to 0 and then your function is Lipschitz or it has some properties, you can prove the existence and the uniqueness of your trajectory or the solution of the ODE. You can't do that with fractional order system. Let's say if I have the same condition, I start from the initial condition and I have fractional order ODE, fractional order differential equation instead of the integer order one, you can't prove that there is a unique solution. You need an extra bit to prove that uniqueness of the solution, which is all about this initialization function. So that's the tricky part of working with fractional calculus, I would say.
Your work has focused on using fractional order systems as modeling real-world systems and how to estimate the system parameters. So I was doing a bit of background reading on fractional order calculus, and it seems like you can also design fractional order controllers. Is this something that you looked at or would like to look at in future?
I didn't look at the fractional order controllers at all. It wasn't part of my research. Whether it's something I would like to look at next, it depends on the problem, to be honest. But what I can say, From the control perspective, you have extra degrees of freedom that you can play with those fractional controllers. If you take a PID or fractional PID, in the PID you have KPK, IKD. In the fractional PID, you have an additional fractional orders. You might think about them as additional degrees of freedom for a controller. Now the question, would you go with the fractional controller instead of going with a more complicated nonlinear controller with the more degrees of freedom? That's a question that needs more research, I would say, to be able to answer. The fractional control part, it is really highly nonlinear. The nonlinearity comes just from the definition of the derivative. You can have really an easy linear system, but because you have the fractional derivative, if you expand the definition of this fractional derivative, it can turn out to be a very complicated nonlinear system.
Just before we move on from fractional order systems to the work that Zehor has done more recently, I wanted to mention some work on fractional order controllers that I came across at a conference recently. So, there's quite a famous formula in control known as the Youla-Kucera parameterisation, which essentially parameterizes all possible stabilizing feedback controllers for a given plant. And these researchers have figured out how to extend this to fractional order systems. So if you had a fractional order model of a system, you could then come up with a stabilizing fractional controller. I mean, I don't know how easy it would actually be to apply this in practice, but from a theoretical point of view, it was very cool. A lot of the work you've done since your PhD has been focused on cancer diagnosis and treatment. So after your PhD, you did a postdoc fellowship. So my first question is, how did this come about?
So the postdoc fellowship, when I was at the end of my PhD, my PI for the postdoc, Professor Alan Tannenbaum, he visited KAUST and he gave a talk. And we were discussing at the end of his talk with my supervisor and another professor, Professor Jeff Sherman. And it was like he was mentioning that we have an open position to work on particular biological problems. And then, Professor Jeff Sherman and my supervisor was said, Zehor, she's at the end of her PhD and she's applying for postdoc. So this is how it came, that postdoc opportunity.
Since then, you've done a lot of work, lots of different areas related to cancer, both on control of chemotherapy treatment and also AI and machine learning, among many other things. Can you start by summarising the role that control can play in cancer treatment?
So control theory has really, I would say, a lot of potential to help in the treatment of chemotherapy and also immunotherapy. However, we are not really at the stage of translation to the clinic, like what has been done with the artificial pancreas, where now we can really see that controllers are used to control the glucose level of patients. And the main reason why control has not really moved forward to the clinic, I would say the main difference between glucose control and then the chemotherapy, the causation effect in chemotherapy, it's much complicated than the insulin. Like for the insulin, we know if you have a low glucose level, like you need to eat more insulin. Like the causation effect between input and then output, it's a little bit more straightforward. However, for cancer, it's really hard because even if you have like the volume, the tumor volume, which is very small, it doesn't mean that that patient is moving towards the cure, because there is like complicated biological effects. Maybe the tumor is metastasizing to another organ and it's still not visible. So the causation effect, I would say, in tumor chemotherapy or immunotherapy, it's much complicated from the causation effect between glucose and insulin. But now with the advances in control theory and especially learning control, I see there is a lot of open questions from the control point of view that can be solved to address those challenges in cancer treatment.
So there's two main papers you've written in this area that I really like to discuss. So one that uses model predictive control and the other that uses impulse control. So the first paper was primarily about modelling cancer growth. Could you give an overview of the main approaches to modelling cancer and whether there are kind of specific advantages or disadvantages of different approaches?
So that first paper, like the focus was more on the modelling and the estimation. The control was there using MPC, but there were like some assumptions on the real life cancer treatment problem from the control perspective. But the focus on that first paper was really on the modeling and the estimation. We have worked on a model which is simple enough, but what was interesting about that model, it was a nonlinear model, but it was a biologically grounded model. So what do I mean by biologically grounded model? It was proposed in the 70s by clinician, and there was like a biological meaning of all the parameters there. And they're related to the, I would say, the fractal concept. It can be related to fractional, but the fractal concept. And the question that I was asked by that clinician when I joined MSKCC, Memorial Sloan Kettering Cancer Center in New York, it's his model. But he said, we have a problem with that model because we have two problems or two questions that he asked. The first one, can you help us into finding a way to estimate those parameters? Because like I said, those parameters have some biological meaning. And one of the parameters, it was like the power. If you have a state x to the power alpha, this is highly nonlinear in terms of parameter estimation. His first question was, do you have a way to help us estimate this parameter in particular? Because it helps us understand a lot about the biology.
So the model that Zehor built on in this paper and used in the other paper that we discuss later is the Norton-Simon-Massagay model, or NSM model. So Larry Norton was who Zehor was working with, and this model has three parameters. So there's the alpha that's just been mentioned, and then there are two other parameters relating to the growth and death of the tumour.
And the second question was, because like tumor growth is very random and it depends on the patient, lot of criteria, can you improve the model to account for those heterogeneity? So those are the two main questions that were answered in that question, in that paper, first paper. So we started by the second question, which is, how can we model the heterogeneity in that tumor growth model that was proposed? And one of the ways, or the straightforward type of models you might think of, is to use stochastic differential equations instead of ordinary differential equation. And you can have the stochasticity part, but we spent quite a few time on how the stochasticity will look like. I won't be maybe diving into too much details, but the choice of the stochasticity function that we have added, it has some meaning with respect to the non-stochastic version. That was in terms of like heterogeneity or adding that stochasticity. But the next question, we know that the tumor growth, it's always a positive. And we are doing our new version of the modeling from purely mathematical point of view. Now, can we guarantee in a sense that our model will keep that positivity? The original model, we know if I start from initial volume, which is positive, the solution will stay positive, which really is not necessarily true for the new model because it's more complicated. Now, once we have proposed the model and then we said, this is a good stochastic model that can have some biological interpretation. Now, are we sure that this model keeps the positivity of the volume? And that was the second biggest part answer in that paper. We have derived some conditions on the added parameters in the stochastic part with respect to the original one that will ensure that whatever positive volume you start with, you're going to keep you will keep positive. Okay, so we started with the modeling. Once we agreed on the model, we said, okay, are we sure, do we have guarantees mathematically that this model is valid for the tumor volume? We have shown that under certain conditions on the parameters, yeah, it can be modeling. And then the last part was on the control and the MPC. But I really need to mention that the MPC part didn't account for the constraints of the control problem. Like, for instance, we assumed that we have measurement like frequently, or we have continuous measurement, which is not the case. But we started with like a first controller that can handle the stochastic model. But I would say that the two main really big questions in that paper was the modeling part, the estimation part, and the positivity. Because in the estimation part, we have a stochastic model now, and then we are happy with it. Now, how can I estimate the parameters of it? With a very few data points in the volume. Like, if you look at the volume in that paper, we have 8 data points, or maximum 10 or 12 time points. That's really few time points to be able to have a reliable estimates for the parameter.
I just wanted to add in a little bit more detail on how this stochastic modelling and estimation works, because I was going to ask more questions about it in the interview, but I couldn't remember what it was called. And the fact that you can estimate parameters using less than 10 measurements is wild. So Zehor's paper refers to something called population mix effect modelling. And essentially this allows you to identify model parameters using extremely sparse measurements by pooling data from a bunch of individuals into a single data set that encompasses the entire population. And then you have another parameter that describes the variation of individuals from the population value. And then that way you can model both population distribution and individual variation with hardly any data from each individual. You recently published a paper on impulse control of that model. I was wondering, you mentioned that MPC was kind of just your first choice and that was not what the paper wasn't really about. So why is impulse control more suited to cancer control?
The second paper, we started looking more into like the real constraints of a chemotherapy control problem. The first one didn't take into account that usually like the chemotherapy it's given intravenously, which means into a very short time period that can be modeled mathematically like in impulses. And the second paper was, this is one constraint from another group of constraints in the chemotherapy control. We know that the control is impulsive. How can we deal with the impulsivity with the nonlinear model we are having? And in that paper, we found that we can have a nonlinear transformation that will allow us to convert an impulsive nonlinear control problem, continuous one, into a discrete linear problem. And that was the purpose of that paper. And now we are working to include more constraints. So that paper, it looked only at one constraint, which is the impulsivity of the input and how we can deal with that with the nonlinearity of the model. Now, the next question is, how can we deal with the sparsity of the output? Because we have an output at very sparse time points. We can have a measurement of the tumor volume every month, every 14 days, every 21 days. From the control perspective, and then having convergence guarantee, that's very challenging because most of the time, assume we have a continuous knowledge of the output. So that's the second constraint we are adding into that impulsive control paper and see how we can deal with the sparsity of the measurement. Now, this is one of the biggest projects I'm working on to really try to make step forward towards translational clinical impact. So we are trying to come up with control algorithm with safety guarantees that include as much as constraints as in the real case scenario. One of the constraints that we didn't start touching upon is how can we deal with measurements that are not modelable or measurable? Like, what do I mean by that? So if you remember from the question of what's really difficult about controlling chemotherapy, it was the causation effect was not straightforward. So now most of the studies, they will assume that the output is the measured tumor volume of that person. But really, that's just one output. And like I said, if it's very small or it's like almost zero, it doesn't mean that the patient does not have cancer. So there are other biomarkers that usually are used in the clinics that help like the clinician to say whether this person has cancer or not. Some of the biomarkers are, for example, liquid biomarkers like blood tests or a kind of serum test. And we don't necessarily have a model for those biomarkers. We know how to model the tumor volume. We have a mathematical model, but we don't have necessarily like a model for those biomarkers. Now the question, in order to solve a control problem that will involve both a modeled measurement and a non-model measurement, how can we solve this control problem? So this is one of those questions that we are investigating right now to see how we can solve that control problem. Hopefully it will, again, make step forwards towards translational, because the next step after we solve that problem would say, can we do like an in vitro testing to test our controllers?
Okay, so just for anyone not aware of the terminology, in vitro testing involves testing things out on cells in a lab environment. And then once you've shown that your approach works in this case, you can then move on to in vivo testing, where you test your approach on animals. Also, for completeness, in silico refers to demonstrating things in simulation, which obviously is the first step in the process.
That's really the first easy experimental test, which is doing an in vitro, maybe organoid test where you have your controller adjusting like the chemotherapy dosage and see if the cells are shrinking or not. And if you have a first proof of concept, this will help us to go to the next step, which is doing an in vivo animal testing. But so we are working on quite a few questions from the control point of view.
My next thing I wanted to, almost the last thing, was about AI and control. Because I know you've written a lot of papers on kind of AI, machine learning for various things related to cancer. How much crossover is there between that work and the work you've done in the control region?
When I started my postdoc, I went out of my comfort zone. I was working in a cancer research hospital where we have those very high dimensional data that clinicians or people there try to understand them or make sense of them. So I would say the postdoc, it was really an opportunity for me to read a little bit more about a field that I wasn't exposed to during my PhD, which is data analytics, machine learning, a bit of graph theory, because I was working with gene networks. And I had a couple of research papers on purely, I would say, data analytics. But really, I think in all the research project I was involved in, the question, it wasn't really about what machine learning algorithm to use to have a very high accuracy. But it was really about having an algorithm or a pipeline that you can explain to the clinician, or it can give them an answer why it's working, why it's not working. So if you see most of those papers, they will rely on theoretical foundation, which is optimal mass transport. Again, that was a new theory that I did discover during my postdoc. So the question was, how can we combine those theoretical foundation on optimal mass transport with machine learning to have an explainable pipelines that will help you? Like if it's given high accuracy, that's good for us, but it can help us to go back and then, for example, try to understand what are the genes that helps into making that prediction. So that's the kind of work I did during my postdoc. It was pure data analytics. How can we have a computational pipeline that can have machine learning or not? Usually most of the paper, they do have optimal mass transport with graph theory. Why graph theory? Because we were working on gene network data. And it has a bit of machine learning for the prediction part. And this combination helped us to have a more robust and explainable pipelines for prediction. Now, my current research, it's really about understanding the link between control theory and AI. Like how control theory can help the AI part and vice versa. Now you will see a lot of research where you have learning part into any controller, like classical control, maybe to learn the gains of the controllers, maybe to learn the gains of the observer. That's one way of like the intersection between AI and control now. The other way, can the control theory as we know it now help into understanding those AI models and the machine learning models and like explain why it's working? Like, I think that's really one of those interesting questions that I'm trying to dive a little bit more into details with my research group. Like, how can we combine control theory with the learning part to either have better control performance, or from the other side of it, it's to help into making the data analytics pipeline maybe more explainable or more robust. So the link in both directions, how the AI can help the control theory, but also how the control theory can help the AI bit, and what's the best way to fuse both of them for a particular problem, especially for the biomedical problems and robotic problems. So that's my current research interest, I would say.
If
If you'd like to learn a little bit more about how control approaches can be used to design robust machine learning models, you can see last month's episode with Matt Turner, who has some very nice papers on designing robust neural networks using strategies typically used in control design.
Do you think when you went into your postdoc and work in the new area of AI, do you think having a background in control gave you a different perspective on the problems you're working on?
So I would say that was a risky jump. Okay, should I go and work on something that I already know, control theory, estimation, and I worked on for a long time, or I will switch. So I think switching at that right time, which I really wanted to understand, and I thought that it was the perfect moment where I can learn something that I don't know. And what helped as well, like maybe having the control background, but also the group I was involved in. Like we have control theorists, I was the only one, but we have mathematicians in the group, we have computer scientists, and those different backgrounds, I think it helps into coming up with those pipelines that you would see. They are not really pure machine learning. It's a pipeline that has a bit of theory. It doesn't have like a bit of control theory, like per se. But I think having that theoretical background from control theory, it helped into coming up with those computational pipelines. I really do believe in interdisciplinarity in research, and it's really important. We can't solve everything by ourselves. Like if I take the example, which is really close to my heart, like the control problem for chemotherapy or immunotherapy, it's not really a work of control theorists. It's not really a work of a biologist, but it really needs the effort of everyone. If really someone wants to make translation to the clinic, and then we arrive at that day where we might think of having a pump maybe for cancer treatment, like what we have now for insulin. Mm-hmm. So yeah, I do believe in interdisciplinarity. I think everyone can feed, like every discipline can feed to the other discipline and have stronger impact compared to like working solely on a problem. So yeah, that's really, I would say, the conclusion I came up with after my postdoc experience. It was a very rich experience. Tough at the beginning because you are entering into a field that you don't know, but after a couple of years you see the benefit, like the long-term benefits.
I have some quick fire questions for you. Is that okay? Are there any control-related research areas you would like to work in that you don't have much experience in yet, or any other research areas?
I think, yeah, the learning control, like I'm still discovering that field. Like I said, I know about control theory by itself and the machine learning, the AI, from the computer science point of view by itself. But I'm really intrigued into understanding a little bit more on the association of control and learning. So that's really one of the areas I want to put lots of effort into understanding and having contribution in that field.
What's your favourite thing about your job?
Being an academic, the first bit of it's the research and then the teaching. I really love teaching, like since I was like a child. I don't know why, but really, like the favorite part of my job, it's being able to help students or to give to the student like the knowledge, and at the same time learn from them, from your PhD students, postdoc, colleague, from the research perspective. So it's a field where we are constantly learning. Literally every day, from the research point of view and then the teaching point of view, and it is enabling you to share what you know with others, with students, with colleagues. So this is really what I like the most about my job: sharing and then constantly learning.
What's your favourite project or paper that you've worked on?
I would say like the cancer one. It was really close to me because of the implication it can have. All the other papers have specific like point that I was interested in, but working in cancer, especially with clinicians, was giving me like really a push to work very hard on, for example, that paper or that project in general. Like, of course, that paper didn't solve, like I would say, maybe 10% of the real problem. But it opened my eyes. There is open questions from the control point of view that needs to be solved before saying, okay, control is really to be deployed in the clinics. So I would say that's one of the research projects that is close to me from the application point of view.
So your work throughout your entire career, a lot of it's been on biological systems. So kind of what drew you to working on that initially? Why is it a field that you're kind of have been actively working in since then?
So I got to the field of biological system, like from the cardiovascular system, because my PhD supervisor was working on that. But I think with the years, and when I started reading more and then being more mature in research, I was interested in two applications, the biological field and then robotics or autonomous systems. Biological systems, it's really like you are working for a problem that you see that maybe one day it will have an impact on others, on people. Maybe not in the short term, but really when I work on such type of problems, I do my best to not work from the theoretical point of view on those problems, but really try to address the real problems. Like I said, it can take years to make an impact, but at least I know I'm working on a problem that it has potential to save people's lives or help them into having a better life. So that's really what I like about working on biological or biomedical in general, that type of applications.
Final question, who is your role model within control or biomedical engineering?
There have been a lot of people who had an impact in my professional career in control. One of them was PhD mentor, and he's part of my committee. His name is Jeff Sharma. Really, he inspired me in the sense of his rigor into dealing with theoretical control problem, and it didn't matter to him whether you're gonna have an output today or 1 month. The rigor he was having, improving or having a control solution that is not just working, but it does have some safety guarantees. So that rigor that he had in doing his research, proving things and making use of the theory he was proposing, or even teaching. I took a course on reinforcement learning with him. I think it influenced me in a sense in the way I try to do my teaching or handle research question.
Thank you very much for the interview.
You're welcome. Thanks for the opportunity again, Lucy.
So, in conclusion, estimation of biological parameters can be really useful to understand what's going on inside the body without having to carry out invasive tests. It's often useful to model biological systems using fractional order models, but it turns out this is so much more complicated than just using integer order models. And control has a very important role to play in cancer treatment, but there's still a lot more work to be done in this area. As usual, I've left links to papers and people mentioned in this episode in the show notes in case you're interested. Thank you very much for listening. I hope you've enjoyed this episode. Please feel free to rate or review the podcast. We also have an Instagram now that I've linked below. Also, just as a little extra aside, since Zehor mentioned being inspired by the rigour of her PhD mentor, I would like to add in here that Zehor is one of the most rigorous people that I know in the way that she works. And this is part of the reason why I love having her as my PhD supervisor. That's all. There will be a new episode released on the 1st of February, featuring my first guest from a university other than Southampton, which is very exciting. Until then, I hope you have a great month.